right? Okay, so just agree between each other. I know it's in English, but whenever you have problems understanding anything in the slides or what I'm saying, if I'm talking too fast, if I'm talking too difficult, just raise your hand and tell me, please explain it again. Even in Italian, okay? So questions and everything, feel free. Try to do that in English if you can. I don't care if people laugh or whatever, okay? Just try to, because that's the best way to learn English for you guys. From a technical perspective, I know it sounds ridiculous to speak English among us, but from a technical perspective, it's a big advantage if you go on the market, on the job market, knowing very well how to use English for your programming activities, okay? So I'm not repeating things that you probably know already. 90% of the documentation you will find around will be in English. Web resources are definitely in English, conferences are in English, so the more you train yourself talking and speaking in English and using it for your work, your career, the better it is, ok? Quanti hanno avuto problemi a capire quanto ho detto fino adesso? Facciamo il contrario, chi ha capito tutto quello che ho detto fino adesso? Ok, va bene. Tu un po' così così? Più o meno. Ok, great. So it seems that you at least have a basis to understand what I'm saying. Okay, so I'm a professor, I'm Marko Bertogna, I'm a professor at the other departments of the informatics department. So I have different courses there, and this is my first course that I give here, computer engineering course, okay? So to me it's a good occasion, a good chance to know more students, to have, to meet, to get involved to the activities that we do in our lab. So my lab is around 20 people now, more or less. It increased very much in the last years. And we are working a lot in real-time systems and in autonomous driving systems, okay? Autonomous driving, cars that drive by themselves, okay? These are one of the most notable examples of real-time systems that you will encounter in the near future, okay? And so my chance, like even if I'm teaching more than I'm supposed to me this course really is something that would like to raise your interest among the topics that we are going to address. So whoever of you will be interested in developing further the topics that we exploit that we show in this course is more than welcome to visit our group, have a thesis, a joint thesis together, tirocinio, or whatever you would like to call it. So we are more than happy to have you guys on board on one of the many activities that we had lately, especially with relation to autonomous driving. Formula Student autonomous, Formula 110 autonomous. We have a nice Maserati that we customize to get and run autonomously, okay? So there are many nice activities that we are looking forward to present to you guys, expose you guys to, and work together on. This is not a course on autonomous driving. This is a basic course on real-time embedded systems. So real-time systems, I will explain a few words, we'll spend a few words today trying to explain you what do we mean with real-time systems. And along the 70 plus hours that we have together, we will try to give you at least some basic knowledge on how real-time systems are made. The course will be both theoretical and practical, so we will have some theoretical formula, demonstrations and proof, which I kindly ask you not to be scared about, nothing so difficult, it's not a math course, coupled with a lot of activities, practical activities that would like to involve you in more system-oriented work. So we will literally learn together how to write a concurrent, a parallel concurrent real-time application composed of multiple tasks on an embedded device such that the real-time requirements are met. Okay? But let's go step by step. Probably most of you does not even know what a real-time system is, or you have like a basic high-level understanding of it. Okay? Okay, so let's jump start to the slides that I used to help me in giving the speech you will notice that I will always use slides that I will make available at the end of the class. Okay, so I will use the Dolly system for you guys to download the slides. Slides are not available before the class, just after the class. Okay. So what is the target of this course? The target, I feel that, okay, we have very nice courses both in the first bachelor program 3 years and in the master program is 2 years. But my feeling was that then one goes to work and encounter systems that are not the general purpose system that you are used to work on. So typically if you work in automotive domain, you will not work on Intel architecture, writing whatever kind of C code that they're used to write. If you work on industrial automation, the same applies. So the code typically must comply with some requirements, especially safety and timing requirements. There are ways to write code that help us avoiding big problems that might arise in our systems, and that I will show you. Okay, I will show you what kind of problems may arise in using concurrent programming in our embedded systems. I know that most of you already gave courses on operating systems, right? Programming, even advanced programming, right? So I am assuming that all of you, please tell me if it is not the case, I am assuming that all of you is familiar with C and C++. Okay, who would say he is not so familiar with C or C++? Please raise your hand without any embarrassment. Okay, so I'm assuming that every one of you is familiar with C and C++, and I'm assuming that every one of you is familiar with the basic operating systems details, okay, practices. I hope that all of you know what is a task, what is a process, what is an interrupt, what is polling, and so on, okay? Just to be sure that you did not forget everything, I will have one class where I remind you all these kind of topics. Okay, we have the summer in between. It's good to refresh a little bit our minds. Okay, so I will re-give you like basic high-level knowledge on architecture, operating systems, and concurrent programming, and we will bring this to the next level. Okay, we will learn how to write a concurrent application, so application composed of multiple tasks in a safe way, so that you don't have critical courses, you don't have deadlocks, you don't have live locks, you don't have all the problems that typically arise in concurrent programming. Let me ask you another question about concurrent programming. How many of you did write a concurrent application before? So how many of you guys did write an application composed of more than one task? No one?
By task, you mean process?
It may be process, yeah.
So, yeah.
Okay. Maybe, okay. Half of you? The basics. Okay,
Yeah,
good. Okay, good. So it's good that you have the basics. So here you will learn how to synchronize, communicate, avoid deadlocks, avoid starvation. So do that in a much more efficient way. Okay? Things out there in industry are concurrent, okay? Even if you work not in embedded application, if you work at Google or if you work for whatever, things are not just one task that does everything. So applications are inherently concurrent, okay? Despite this is not an operating system course, I found it necessary to strengthen your knowledge on concurrency, okay? So you may ask, why are we restudying some of these things, okay? Because we are bringing them to the next level. So I'm really trying to make the problem as complex as possible for you guys to make familiar on what kind of problems may arise in an industrial setting. Once you are strong enough in dealing with concurrency, we will start with the real-time systems part, okay? So first of all, management of task concurrency, synchronization, communication. We'll have a few classes, okay? And once we are set with that, we will proceed to the theoretical basis of real-time systems. scheduling and schedulability analysis. We will see what does that mean. So scheduling, if you have multiple processes, multiple tasks, you need to decide which one of those tasks execute at each time. Okay? The scheduling policy significantly affects the performance of your system as well as the timing predictability of your system. So the way I decide to schedule task 1, 2, 3, 4, 5 affects the time it takes for your application to execute and to meet the timing constraints that you have. Okay? So in a real-time system, just to start understanding what do I mean, we never want that you have an experience like in your laptop where you open a window and it takes forever to open. Okay? So things in applications, processes, in a real-time system setting need to have a response time which is predictable and always happens before a well-defined deadline. Okay? This is the main target of a real-time systems. We will go slowly into that. Schedulability analysis, this is more a theoretical concept that provides you analytical grounds, analytical evidences, proofs, theorems that assure you that it will never happen that a task finishes after its deadline. Okay? You may think, why is that useful? Why cannot I just use a faster processor? Or why just allow him to miss a deadline from time to time? There are multiple reasons why this is not possible. This is a Modena and Bologna. It's a very industry-intensive area. So let's bring together with us along the whole course two examples, automotive and industrial automation. Automotive and industrial automation. In automotive, you have a certain kind of systems which need to be qualified according to the highest safety standard. Okay, you have some control engine, you have electrical steering, you have engine control, you have all the chassis and all the gear processing, il controllore delle marce, della frizione. You have all the activities, applications which are implemented in embedded controller, which is not possible for them to fail. Can you imagine what happens if something fails in a car that is running 130 kilometers per hour? So this application required to be qualified according to some safety standards. One of the mostly used standards in the automotive sector is called ISO 26262. Is there any? Yes. So this is one of the most widely adopted safety standard in the automotive domain. It's a series of requirements, of recommendations that your software should be subject to. For instance, avoid the use of pointers, avoid the use of unbounded loops, avoid the use of a lot of fancy things that you learned how to use in your previous courses. Avoid dynamic memory allocation, avoid the new malloc and this kind of stuff that we are used to use, right? Why is that? Because these kind of paradigms, these kind of programming practices are inherently unpredictable. You probably learned that a malloc or a new may fail, right? You know what a malloc is, right? Yes. So it may fail. If there is not sufficient memory, the outcome can be negative, okay? I don't have memory where to run my engine control system. If I use a pointer, there are many problems related to pointer, like dangling references, null pointers, and so on. So there are really many problems that may endanger your system. More than that, you really need to guarantee that your task finishes within a determined deadline. Okay, so there are a lot of practices that should be accomplished, should be followed in order for the automotive system to be guaranteed. Industrial automation, same thing. Industrial automation, we have many companies, Acme, IMA, GD, Tetra Pak, we work with them a lot, Comau, all these kind of companies are leading companies, really world-leading company. Tetra Pak is a leader, IMA is a leader in his domain, GD is a leader in the packaging of cigarettes. SACMI is a leader in automation for ceramics, tiling. Okay, we really have a very strong industrial background here that in academy we don't teach how to interact with them. So you know a lot of computer science, but you don't know how the really industrial systems are made. So there, imagine this kind of machines can have labeling systems or packaging systems that work at, 1,000 packs every seconds. You know, if you see this cigarettes machine, they're really boom, you cannot even see the cigarette going, so fast is the system running. So all these kind of systems are controlled in real time. What happens if your control of the cigarette placement or of the package placement or of the tile placement does not happen in time? It happens that you should discard that component. It happens that the machine can block, affecting production. It happens that it doesn't do what it's supposed to do. Okay? All those systems are real-time systems. They don't use Windows, they don't even use Linux, but they use a real-time operating system. They use a real-time operating system that is more suitable to be predictable. There are stronger guarantees to achieve the timing constraints that you need to enforce. Okay? So, we will take a look at a real-time operating system in this course. I will show you an open source real-time operating system. It's called Erica Enterprise. It's by an Italian company that provides this system for a lot of automotive components from, for instance, Magneti Marelli. Okay? They don't use Windows, as you guessed, they don't use Linux. They use real-time operating systems. We will see what is there in a real-time operating system, which is different from the operating system that you saw in the previous courses. Okay? Nothing more complex. The opposite. It's a much simpler operating system that doesn't have unpredictable features. Okay? It is typically very small. It's a microkernel-like paradigm that is essentially a smart scheduler that tries to schedule things in a more deterministic way. Okay? We will have the chance taking a look at these operating systems. Okay? I would have loved to have you guys using also embedded boards where to program them with a real-time operating systems, but we don't yet have the support for such boards. Okay? So for your projects, we will still use the laptop that you guys have. Okay? There will be a project, I will tell you later. But for those projects, we will use Linux and pthreads. Okay? So we will not use the real-time operating system because it requires a special board or ARM-based microchip or Freescale or whatsoever. We do have it in our lab, but we don't have it for all of you guys. So for the project that we will develop together, you will use your system, your general purpose system, using Linux and pthreads, just to test your skill in dealing with concurrencies, with scheduling, pthread, shared resource access, and predictable use of libraries. Okay? But the real system use a real-time operating system. Okay? So last point, as I just mentioned, there will be a project to be presented at the exam. Okay? So at the end of the course, you will be able to write your own real-time application. You will be able to write from scratch a full real-time application composed of multiple tasks that communicates and synchronize between each other, make a predictable use of the resources. What is a resource? Resource can be something in memory, a memory object, can be the screen, can be a task of your game, can be a controller that you make, can be a simulator that you use to simulate your drone flying system, whatever, okay? So you will need to predictably use and communicate and synchronize on the access to shared resources. So you will both schedule the tasks that you composed, the concurrent tasks that you composed, that you wrote. You will both schedule them on the core or cores that you use, and you will schedule their access to the shared resources. Being able to do that in a good way is, of course, something that is very valuable in today's industry. Just to mention, I'm always open about that. We have a few contracts with industries that don't have programmers able to deal with concurrency, okay? They just say, okay, we had this task before, now we port it to a multi-core system and nothing works anymore, okay? How comes? Yeah, that's exactly the reason. We'll see here. Just writing an application concurrently imposes so many problems that if you are not trained to solve them, you don't know where to start, okay? Nothing so difficult. You will have problem in solving some of the exercises that I will give you, okay? But once you solve them, then you're good to go for it, to industry, okay? Then you're good to make an application parallel, make an application concurrent, and more predictably exploit this parallel computing architecture which we have today. Multi-core, many-core, GPU, and so on. I mentioned before, why not using the same task as before, but using, like, increasing the frequency of your controller, of your CPU, right? So if you have your tasks and you notice that the deadline is missed, so let's try to run the processor faster, right? That's what has been done until yesterday in single core systems. From generation to generation, you had the frequency of your CPU, of your core, increasing. You're probably too young, but I remember that the first processor had a frequency of 1 megahertz, okay, mega, not giga, okay? And then we went to 2, then to 4, then to 40, 80. You know the frequency of today's cores? 3, 4, right? The laptop are between 3 and 4. And it has been 3 and 4 since the 2007. It's 10 years that the frequency is stuck there. You know what's the reason? Why is the frequency cannot be increased anymore?
We have multiple of the processor.
That's not the main reason. That's the how to sidestep the problem, right? I can spend a few words explaining to you guys. So basically, you're an engineer, so you probably know that power consumption, and consequently thermal consumption goes with the square of the frequency, right? So if I increase the frequency by 10, the power consumption increases by 100, right? So what we had, I can show you some graph, I don't have it here with me, but maybe next time, I will show you a plot showing the power consumption of the core since the 8086 until now, just taking the Intel, okay, generation. And it really increases exponentially. Like the Moore's law, you know the law of Moore, right? The Moore's law that essentially predicts, it's a self-fulfilling prediction that says that every couple of years the density, the transistor density is double, okay? So you have an exponential increase in transistor densities. What does that mean? That transistors are smaller and smaller. That to communicate from one transistor to the next one, it takes less because they are nearer, okay? So if you have a transistor from here to here, and then I have it here, then the communication latency is smaller, then you can increase the frequency, right? That was happening until now, right? Until the 20 nanometers or 15, or now we are going to 10 nanometers. So since they are closer, you can increase the frequency. So that was, we called it the free lunch, il pranzo libero, il pranzo gratis si chiamava, the free lunch. So everyone could use the before application, port it to the new architecture, and everything was running twice as fast. What happened then? In 2007, Intel had this project called Texas, the new core in the line, which was a single core running at 8 gigahertz. They were never able to implement it. because the power consumption, more the power densities, the thermal density was incredibly high. So they needed to have some cooling system that you encounter in a nuclear controller. So the power density was the same as the one you have in a nuclear reactor. Okay? So already the one you have in 3-4 gigahertz is the one of a hot plate where you cook eggs. Okay? You probably noticed the fan on top of it. It's a big fan compared to the standard that we have. So it is not possible to dissipate the thermal power created by increasing frequency further. Okay? But Moore's law continues. So what do we do having a higher density of transistor if we cannot use it for increasing frequency? And that's the answer. Go to multi-core. So use more cores with a smaller frequency. Okay? So that's why we started having dual core, 4 core, 8 core. In our lab, we have a chip of 256 cores. Okay? We have the GPUs. You know what a GPU is? Graphic processing unit, NVIDIA, AMD, stuff like that. We work a lot with them, and they have these very tiny cores, and they are able to put 2,000, 4,000 together in the same chip. Okay? They have a very big competitive advantage nowadays because they understood this path much earlier in time. So these graphical chips were used for, of course, graphic processing, rendering, VR, whatever you want. But now are used for everything. They are using it for autonomous driving, for neural networks, deep learning, whatsoever. So it's the only way out for achieving more performance without sacrificing the power and the thermal consumption. Okay? So what is the bottom line of this talk that I didn't make in my agenda today, but the bottom line is that you will have to deal with multi-cores. You will have to deal with many cores. Many cores are typically chip of 20, 60 cores in the same chip. Okay? How do you exploit a many core if your program is not concurrent? There is no way, right? You can use 1,000 cores, but if you don't have concurrency, if you don't have intrinsic parallelism, you will have the same performance of your single core architecture. Even smaller because we're running typically 1 or 2 gigahertz instead of 4. Okay? Just to give you the idea. So that's why I will insist a lot in this concurrency. This is your competitive advantage when you will go to industry. There are not many people that are trained to do so. Okay? Unfortunately, I will not have time to give you other classes that I give in the other courses of the other department about parallel programming. It's not just about concurrency in real time, it's also about understanding to use parallel programming models. OpenMP, CUDA, OpenCL, OpenGV. There are many parallel programming paradigms that are designed to make you able to let you exploit the parallel computing power of these next generation devices. Okay? But at least you will know how to deal with concurrencies and p-threads, which is still a very good start. Okay? Questions to what I said until now? Okay, so just a few slides about the course outline. Probably most of the things here will not ring any bell to you, but just to give you a set of titles that we are going to deal with along the course. This is just a reminder, just a very brief survey of what you guys already know, okay? Just a few notions of architecture, CPU register, memory, polling versus interrupt servicing, the difference between process and thread, okay? One class we go over all of this, and then we will start the heavier concurrent programming part. So we will tell you, we will show how to make a proper communication and synchronization among the tasks. So in a way that doesn't lead to deadlocks or other kind of race conditions or any problems that may arise. Notion of scheduling. We will divide among between these two categories, shared memory system and message passing system. So these are typical systems that you encounter in our latest course, where you have multiple cores sharing the same memory. Okay? So the memory is one, all cores see the same memory. Okay? While message passing are more concerned with distributed memory paradigms. So you have separated nodes, everyone with his own memory, and if they want to communicate, there are primitives, there are different paradigms, message passing paradigms that allow you to do so. We will see that you can implement the same feature in both paradigms, with difference, of course, implementation, but with different performances. In shared memory, we'll restudy, probably this you already saw, mutex, semaphores, critical sections, monitors, plus condition variables, and private semaphores, which are a way to deal with concurrency, avoiding starvation, okay, that you will learn well. Also, the written exam will have to do a lot with this part, okay? I will tell you about the exam in a later slide. After that, we are ready to start the theoretical part on real-time systems, okay? Understanding how do we model the tasks, the threads that we have in our application, okay? We said if an application, my game, my controller is divided into 8 threads, okay? How do I model each of these threads? Typically, these threads need to do periodic activities. It's not a batch system. It's not a simulation that you run it, it's over, and nothing more to do. Here, typically, in industry and automotive, these are recurring tasks. These are activities that you need to do every period, at least every period, okay? So these are recurring activities. If you have multiple of these activities, each one with its own period, each one with its own execution time, the problem on how to put all of these together so that all deadlines, all timing requirements of each individual activities are met, it's a scheduling problem. Okay, so we will understand together how to schedule these tasks, each one with its own deadline, each one with its own period, so that all deadlines are met. Okay? What kind of scheduling algorithm will we take a look at? Many of them. First come, first served. Shortest job first. Round robin. Fixed priority. Dynamic priority. Earliest deadline first. These are all algorithms. From a less real-time oriented to a more real-time oriented. Okay? We will tell about preemptive algorithm, non-preemptive algorithm, limited preemptive algorithm, and the relation these kind of policies have on the overall response time of each task. Then, so here we just schedule the processor bandwidth, the processing bandwidth. But I told you, it's not just about scheduling processor. It's also about granting access to shared resources. What if two tasks would like to access the screen? Okay, we need to communicate and synchronize all of these tasks. We will show the priority inversion problem that may arise every time two tasks try to access the same resources. Maybe in a car, two tasks try to access the CAN bus. CAN bus is the bus that is the backbone of your car, is the electrical backbone of your car. If 2 or 4 or 6 or 100 tasks try to access the same CAN interface, you may understand that you will need to avoid a race condition, you will need to avoid conflicts, you will need to schedule them appropriately based on the priority and based on the deadline, on the time requirements of each task. And these are the shared resource protocols that we will take a look at. Non-preemptive protocol, highest local priority, priority inheritance protocol, priority ceiling protocol, and stack resource policies. Okay? We will see all of them in the future classes. Okay, I decided the scheduling. I decided the shared resource protocol. Now, how can I be sure that each task will finish before its deadline. Okay? You may say, okay, let's try to run it. We run it 100 times, we run it 1,000 times, and if no deadline is missed, then I'm okay. Wrong. This is not the case in a real-time system. You don't have any guarantee that your system will never miss a deadline if you run it X times. This does not happen, okay? It may be a hint, it may provide you some data, but it's not the definitive proof that you can use when needed to certify, to qualify your system. Running a task, running a set of tasks, running your application 1 million of times does not give you any analytical evidence of that the deadline will never be missed. You have a system here that runs on potentially millions of cars. There are real-time operating systems that are running on billion, not million, billions of cars. By the way, the most widely used operating system in the world is not Windows, nor even Linux, it's a real-time operating system. Because it is featured in all cars you have around, because it's featured in many handheld devices, because it's featured in a lot of embedded objects that you have in your daily activities. Okay? There is the RTOS by Bosch, ETAS. It's used in tens of billions of automotive components. Okay? More than the people in this world. Okay? So how do we make sure then that the deadlines are not missed? We need to provide analytical evidences. We need to talk about schedulability analysis and WCET, worst case execution time. We will need to reason in terms of worst case situation. The worst case reasoning is the typical mindset of a real-time programmer. Okay, you don't assume that things will likely go well. The contrary, you will assume that if something could go wrong, it will go wrong. This is Murphy's law, you know, the law of Murphy, la legge di Murphy. That's a typical assumption for real-time operating system. If something may go wrong, if two tasks may be memory contended, they will be memory contended. That's a possibility, right? So you will always need to assume the worst case situation. I will show you how we can prove schedulability test. How can we make guarantees that task will behave as planned? Okay? This is the schedulability analysis part of this course. Schedulability analysis is based, again, on worst case conditions, on identifying scheduling anomalies, on understanding what is a critical instance, so what is the situation that leads to the worst case possible instance, okay, to the worst case possible response time. Okay? We will show you analytically what are the critical instances of the problems of interest to us. The test that we will derive will be based on utilization, will be least upper bound, will be based on the response time, will be based on the process of input. We will have time to go through all of this. Last, we will see the concept of real-time server. Servers are not the network servers that you may have heard about. Servers, the real-time servers are a way to encapsulate our activities, our real-time activities, in order to provide some kind of isolation, of timing isolations of our activities. Servers are typically used to guarantee that even if you have a misbehaving task, it will not affect the other tasks. Okay? One of the problems that you may encounter when you work on a concurrent application while providing real-time guarantees is that, okay, I design my system so that all tasks are okay. But what if one of these tasks got stuck, okay? Or try to monopolize the resource or behaves different than what expected. We would like to isolate it so that it will not affect the timing guarantees of the other tasks, okay? What you use in this sense are real-time servers, okay? Okay, then This part, the more practical part, I will not directly follow it. I asked Roberto Cavicchioli, assistant professor in my group, to help you in that. So this will also require you guys to have a laptop to use. I hope that all of you have a laptop to use. I assume that all of you have a laptop to use. Tell me if this is not the case. Okay? So when we will start the more practical part, we also have the lab booked for our practical classes, but it's best if you also have a laptop where you can configure and everything also to try it at home. So we will show you examples of real-time operating systems, okay, in particular this ERIC Enterprise. We will show you or remind you how to use the POSIX standards, in particular the pthread programming, creation, join, scheduling, mute, semaphore, condition variable, and so on. Okay, so you will play a bit with pthreads to test also the concurrency problems that we will deal with together. Okay, so you will be given all the details and instruction to get an environment up and running. Plus, we will provide you plenty of examples of possible projects, of possible real-time applications, okay, starting from the simplest possible tasks, maybe 3 tasks that concurrently write on the screen, bouncing balls that concurrently write themselves on the screen, and so on, up to more elaborate settings with the autonomous car in a simulation scenario, and so on. So Roberto will help you try to configure and understand deeply all these applications, all these concurrent applications together. Okay? I don't know, just to show you what kind of application shall we expect. So these are possible projects that there are plenty of those. This was taken by a course, I'm coming from the Sant'Anna University in Pisa. This is a professor, Giorgio Buttazzo, which I credit for some of the slides that we'll see here in this course. And the typical requirement for a student is to build up in groups of 1 or 2. I will apply the same setting here. One of these projects. Okay, it's too early to go through them, but you can see what is it like. For instance, highway. Simulate a portion of a highway where different types of vehicles, motorbikes, cars, trucks, are created by the user as interacting tasks. Each type of vehicle is autonomous and has different driving rules. Trucks cannot surpass other vehicles and have lower speed limits. Vehicles have different sensors to detect the road borders and the other vehicle. The highway can be displayed from top, and the user might be able to zoom or track a specific vehicle. Now you are probably having headaches. Will I be able to do all of this? Yes, you will. Definitely you will. It is not like a real setting, it's a simulated setting, of course. I don't want you guys to play with real trucks, but we will give you all the grounds, all the supporting material to be able to do so. Okay? So I'm really happy. This is more a thing to get you involved, to get you play with things. This is the only way to learn from my point of view, okay? But you are free to propose any project, okay? This is just a possible list, potential list: fireflies, ball beams, segways, goalkeeper, lamp, elevators, Kalman filters, pool, fireworks, radar tracking. These are more kernel projects instead. These require you programming skill at OS level. Try to implement a new scheduler for a new scheduling module for, I don't know, ERIC Enterprise, for the ERIC real-time operating system. Or using Arduino. I think all of you know Arduino. Or drone projects. Drone projects, we will use a drone simulating setting. You can do your drone controller within this simulated setting. Or multimedia projects. Okay? So that really you are free to decide whatever you would like to. Okay? Again, these are applications that comes inherently with some concurrency in it. Of course, you can implement tracks and car everything in one single task, but it will not run as smoothly. Okay? It will flicker, it will jag, it will not work smoothly. Okay? By concurrent programming, you will see that everything works much smoother way, a much smoother way. Documentations. Okay, most of the things will be available on the slides of the course. There is no need to buy anything. Okay, there is no need to buy anything. If you want to buy something, that's the course of the professor I mentioned before. It was my PhD advisor while in Pisa, and probably is the most cited books in the real-time literature. Okay, so hard real-time computing systems. This is the 3rd edition. Okay, you don't need to buy it. Okay, if you want to buy it, but you don't need to. Okay, and the last is the most important one. So this will be input in Dolly. Okay, the slide decks. Okay, this is the book, and this is the most important feature, especially for your project. Try to independently use web resources. Try to independently see documentation of the libraries that you're going to use. Try to independently use the man pages, the manuals, whatever you want. Independently, don't ask me. I've not been able to use. No, the project is by yourself. Okay? You can ask me whatever we will do in the course, but the project, it's you. Okay? The project, you will not ask me anything on the particular library that you decided to use. If you use it, you check the web resources, you get mad at that forum because one of the guys had a similar problem. Okay, this is the way computer science works nowadays. Okay, you need to be collaborative. You need to be able to access web resources. You need to be able to access forums. You need to be able to make the good question to the right people. Okay, so for the project, you will be for yourself. Please ask me whatever else you want. Okay, the course, on everything. Okay? The project is when you get independent. It's our way to check whether you reached a sufficient independence level. Okay? So, web resources. Allegro is one of the library. Did any one of you use Allegro before? You did? You did? Okay. So you may know that Allegro is good to as a means to build the games or visual interfaces in dynamic visual interfaces for building projects. Okay, typically the students in my first year course they do games with Allegro, not concurrent games because I didn't teach them concurrent programming yet. But they use Allegro to do Pac-Man, to do Tetris, to do all these kind of things here. Okay. It's a conveniently easy library to use for this purpose, but you may of course use whatever you more feel like. Okay? OpenGL or Unreal. Unreal is, I don't know if you guys know Unreal, but it's a 3D simulation scenario that you can use for a lot of fancy things. Okay? So you're open to use whatever tool you would like to. Okay, exam. Exam, there will be 3 parts. So the real-time system parts, which is the theoretical part, scheduling, tasks, shared resource protocol that we just said, okay, all this part here is an oral part, okay, will be oral exam. But towards the end of the course, I will try to make a compitino, like, just to use the same terminology. So a written exam in one of the classes that we have. So whoever passes that exam is exempt from the oral exam. Okay, again, real-time system part is by default an oral exam. Okay, when you defend your project, which is the oral exam, you will also be given questions on the real-time systems part. Towards one of the last 3-4 lessons, classes, we will have also a written exam on this real-time system part, which is optional. You may decide to give it or not to give it, okay? If you pass it, then at the discussion of the project, you will not be asked about the real-time system part. Is that clear enough? Okay, whoever has doubts on it? Okay. Written exam, instead, the real written exam is it's a problem about synchronization and concurrency. Okay? The typical problem can be, if I have 8 tasks and I would like that the first one talks to the other 2, which before needs to trigger the 4th and the 5th starts. So this is the typical way the exam is made. So you will need to synchronize a number of threads so that the specification of the exam are satisfied. Okay, it's a synchronization problem. You will use semaphores, mutexes, condition variable, private semaphores, whatever, that we will learn in the first part of this course. Okay? Projects are not as easy, exercises are not as easy, but we will provide a sufficient number of them to get you acquainted with it. Okay? So I will show you 4 or 5 different examples of synchronization that hopefully will make you sufficiently expert to pass the written exam. Okay? So, oral exam, real-time system, but with intermediate written exam that exempt you from it. Written exam is mandatory on the concurrency part, okay? Nothing special. You just need to do a few exercises, but you will need to do them, okay? And the most important part, the project, okay? The most important part is the project. There is not a particular rule to do the project, okay? I gave you 52 examples before. We will have time to go through them, especially Roberto will take care of this part. So it's a project that uses P threads concurrently, synchronize themselves, and you may use a graphical interface like Allegro, okay, to build your game, your controller, your simulated environment, or whatever you feel like doing, okay? Should be not too complicated, okay? It's not a thesis, okay? Don't waste more than the needed time, but not even too simple, of course, okay? I would like to see some of your abilities, even in proposing something fancy, something cool for you, okay? But it's also a time for you to have fun. So do something that you like. You like games, do a game. You like controller, do a controller. You like a database, I don't know, try to figure out about a way to concurrently use databases, okay? So you're free to do whatever you like. You have experiences in Qt, graphical interface, use the Qt, okay? So it's up to you to use whatever you prefer to. I see that typically students have fun in it, okay? Questions? Yes?
Come vengono valutate le parti?
No, prima in inglese, dopo se hai problemi senza paura, buttateli, anche per dare l'esempio agli altri, anzi, peggio lo dici meglio è. Scusa se ti metto a disagio, non? Evaluate.
How do parts evaluate for the exam?
So, the idea is that they count in a fair share. So I will make an average on the 3 parts: real-time system, concurrency, and project. But the real thing is that I always get more biased in favoring the project. So the project can compensate a little bit what you earn in the previous one. So typically I notice that I'm much more stricter in grades in the written parts. Okay, I tend to give low scores in the written parts because there is always something that you guys mess up with. Okay, and with the project I try to compensate. Okay, so the fancier the project, the higher the thing. I can even go above average, above the computed average, thanks to a good project. Ok? Poi che lo scrivo in italiano?
Sì.
Allora, facciamo un'eccezione. Allora, le 3 parti valgono uguale e tipicamente faccio una media, ok? però di solito tendo a valutare molto meglio il progetto, quindi va anche al di là della media. Quindi se uno ha 18 alla parte real time, 15 che è il minimo alla parte di concurrent programming, okay? La media fa 16-17, poi mi fa un progetto da 30 lode e gli do anche 27, per dire, ok? E quindi se proprio il progetto è molto figo, hai capito? Cioè, vedo che ci ha lavorato, ok? Ci siamo capiti. Se no in generale faccio la media tra le tre parti, ok? Si parte dalla media, poi posso andare più giù, più su, insomma, vediamo, ok? Other questions? Yes?
The oral exam and the written exam are both in English.
Oh, good question. I didn't think about that. Yeah, I think so. Yeah, I'm sorry about that. Yeah, it should be in English. Yeah, sorry about that. But of course, I'm here to help you guys. So if you have problem writing or whatever, I will close an eye. Okay? Non è un'espressione inglese, close an eye.
So in the second part, we won't be using a laptop.
In the second part, you will not be using a laptop. Yeah, just on paper. Sorry about that. Yes. Well, I can make an exception though.
Yeah, that.
When I give that exam, the answer was no, was written.
So we can check.
But you can take with you whatever you want. So you can take with you everything. Okay? You can give notes. You can have notes. You can read. You can not communicate with the other one. You cannot have. The only problem with having a laptop or something is that I need to make sure that you don't communicate with each other. But I mean, potentially you can even have a laptop with you. Potentially we can organize it with a laptop, okay? So for now, assume it is written, and you can take with you whatever notes you would like to the book, you can take with you whatever, okay? Hai capito?
Yeah.
Okay.
I think by using a PC would be much simpler for us, like we check.
Yeah. The point is that I don't know whether for the exam we will have a room that will guarantee me that you will be able to perform the exam without communicating with other people, so it makes a little bit more overhead on my side. But let's see.
What's the duration of the written exam?
Oh, it's to be defined, let's say typically a couple of hours. It's one exercise. I can show you some of the previous exams, just to let you know what I mean here. Okay, this is like a typical exam. This was in Italian, it was not an English course. A multi-thread system simulates a car competition. There are n threads. Each one simulates one of the cars racing. The track is modeled by a data structure called track, and the track manager by a thread manager. The picture is like in figures. There is a start function which is blocking. All threads are blocked until the thread manager gives the go, the green light, the function run. Okay, so you understood the kind of problem that we need to solve. Okay, now it's a little bit too early to focus on it, but it's just one problem that you have 2 hours to solve. Okay, tentatively, let's assume we solve it on a written form. If I will be able to set up some infrastructure, we will do also with the help of that. Yes.
Will these examples be available on English?
Yes, at least 5 of them or 6 of them, as many as you want, okay? Other questions? Okay, tentatively I will start 15 minutes later, especially when we need to start early on in the morning, because I come from Mantova, which is quite far away. While in the afternoon, let's try to start more or less in time, especially tomorrow that we have the class very late. So we have the class at 4, right, tomorrow? Yes. So on Friday, I think we start at 9. Let's start 9:50ish. Okay? 9:15. Okay? 9:15. What else did I forget? Everything is clear. Okay? I'm available here. Reception, just drop me an email. Okay, for the reception hour. Reception hour around Wednesday or Thursday, I forgot. It's on Dolly, but I mean, you know, it's on the page of the course. But you can feel free to write me an email as if you have some questions. Yes.
Maybe we write in Italian by email.
No, in English. So I will receive less email, which is also good. And you can also address directly Roberto Cavicchioli, which is, you can write both me or Roberto. Okay? Roberto will follow you more on the project part. Okay? On the theoretical part, feel free to write me. For the practical project part, try not to write, but you really need to write Roberto. Okay? Okay? Shall we start? Okay. This is not the real-time systems part. This is just to give you an introduction to understand what are we talking about. Okay, so the first 40, 50 slides are just to give you a big hat upon which putting all the things that we will develop in this course. Okay, just to give you some understanding why do you need to study real-time systems, which is something that you guys didn't do up to now. This is my email, by the way. Name, not surname, give me more. The K before you ask it because I was born in Croatia, okay? It's not just because my parents were crazy. Okay, what is a real-time system? A real-time system is a computing system that it is not sufficient that works correctly, but it should answer, it should have a response before well-determined timing constraints. So it is not sufficient the program to be functionally correct, it should be also timing correct. Okay? So it's not sufficient that the answer will be the right one sooner or later. The answer should be the correct one in time. Okay? This is in a few words a real-time system. Okay? Not only functional correctness, but also timing correctness. Nothing beside that. Okay? So they typically are associated with embedded systems. What is an embedded system? It's a computer that is embedded into an object. Take a car. A car is an object. Inside the car we have a computer. Okay? Your mobile phone is an embedded system. Okay? It's ever more coming a general purpose system because they really do everything now. But initially it was an embedded system. Okay? Whatever kind of controller, the VR tool set that you have, it's an embedded system. It has a chip in it. There are plenty of embedded systems. Even a plane is an embedded system. Actually, planes, avionics systems are the typical example of real-time systems. Automotive, industrial automation, avionic, and unfortunately also military. Okay? Also military are embedded systems. Nuclear power plant are embedded systems. You need to control the reactor, the nuclear plant in real time, otherwise something very bad may happen. So typical real-time systems are embedded in a bigger object. It may be small, like a cell phone, maybe huge, like a plane or a power plant. Okay? Anyway, they are embedded systems. So, an embedded systems, how do you control a system? We work now on autonomous cars. Okay? I can make the example of the cars that we use in our lab nowadays. We have this project called Formula 1 10th. It's a scale model of a car that will participate to a challenge, an international challenge, in two of the biggest conferences in our domain. And all the groups in the world will compete with the same electric motor, with the same sensors, with the same processing boards. They will just be evaluated by the algorithms and timing of their decisions for the cars, sensing the environment and independently, autonomously moving in a given track. Okay? So this is an example that we have a couple of cars. They are equipped with sensors and actuators. Okay? So that's a typical embedded examples. So in order to control this system needs to know the environment. How do you know information about the environment? To know information about the environment, you need this. Okay? You need sensors. Sensors are the only door for your system to the environment. Okay? It's the only way that your system can raise the awareness of what is happening all together around and modify its behavior based on it. Okay, so the typical way an embedded system works, you have sensors, maybe a camera, maybe a LiDAR, maybe an inertial motion unit, IMU, maybe a LiDAR, maybe a radar, maybe whatever. Okay, you process it in an embedded computer, hopefully in real time, and you act on the actuators, on the motors. For instance, you change your steering angle, or you decelerate, or you accelerate. Okay? These are actions that you need to take in real time. Why is this important to take this action in real time? Why is it important to close the control loop within well-defined deadlines? We experienced it in our vehicle. It's very easy to show you guys. We had the first prototype that the student made up was taking the curve and steering well beyond the curve. Why is that? The curve was properly detected, but the signal was sampled here. Then it was being elaborated. Then here you notice that there is a curve. Here it provides the new steering angle, and here the steering angle gets actuated, right? So if the time from sampling to decision is too long, it affects the way the system is controlled. Okay? This is a very basic example. Same in the industrial automation process. If you have a labeling machine and the actuator act too late, maybe the bottle already went away, or maybe the label is put in a wrong position, or whatever, you name it. Okay? So this is of uttermost importance for real-time system to have. I mentioned you that the number of electric systems is exponentially increasing. So in the 70s, this was particularly important for avionics systems. We have the planes flying around, which were hard real-time process. It could never fail. It could never compute something beyond the deadlines. Otherwise, the plane might potentially crash. Then we had the division of robotics. Then the automotives and industry 4.0. Okay, multimedia. Okay, that's an old part, but all the multimedia stuff and embedded board we have. Really, we have billions of embedded computers. Let's compare the number of embedded computers we have around with the number of people in the world. So the green curve tells you the increasing of the population in the world. You may know we are around 7 billion people in the world. Okay? Below here you have the number of PCs. This is an old slide in the 2000, but the trend is more or less continuing that way, in a linear way. Okay? You can see we don't reach 1 billion of PC, of personal computers. Okay? While the number of microprocessors, the number of embedded systems is exponentially increasing. So really we have billions of devices featuring an embedded real-time operating system. Actually, today, 98% of the processors in the world are embedded processors, are embedded in other objects. Cameras, iPods, cards. The cards has an embedded processor inside. Microwave, set-top boxes, HVAC, so the refrigerators, washing machines, cars, you name it, okay? All of these are embedded devices. 98% of the computers in the world are not personal computers, are embedded systems. An example, what are the embedded systems in a car? I don't see any. Well, there are plenty of it. There are hundreds of it. One of the most important in the future will be the by-wire, X by-wire. It can be steer by wire, accelerate by wire, brake by wire. also in the plane is the same. So there is not a mechanical direct connection from the steering to the actuator, but it can be mediated by an electrical signal. Okay? This spares you wires, this spares you, mechanical parts. This allows you to control electronically your steering. Okay? It's not yet like this, but it may be like this. Okay? So that you will have a sensors here. Okay? For an autonomous car, you will have a sensor here in the steering wheel that will tell you the position. Okay? The control unit will read this sensor and maybe actuate this position, the wanted position on the actuator here. If you have an autonomous driving car, this is automatically computed by the vehicle controller, okay? It will automatically steer this and this. And they should be perfectly synchronized if the driver would like to retake control of the thing, okay? And you cannot have a glitch, you cannot have a delay. You cannot have a fault here. Imagine what would happen if for some reason it thinks, okay, let's steer 90 degrees now, okay? No, this cannot happen, okay? It should be correct and in time and synchronized perfectly between the two parts. And we pay here the typical price of this increasing complexity. So the number of lines in the computers, in the ECUs, in the vehicle controllers, in the embedded controllers that we have in our car is exponentially increasing. We have a huge number of functionalities in nowadays cars. So it is difficult to design such complex systems. We have really hundreds of runnables of tasks running on our cars. It's really becoming a messy problem to design such a system. Predictability, so the more complex you get, the more difficult to be predictable. It's easy to control something with a few lines of code. You can, by hand, even understand well everything, but as long as the number of ECUs increases, it's becoming a mess. Less reliability too, okay? How can I make sure that everything works as planned, that everything is reliable, okay? So one of the approaches is using component-based design. This is a common paradigm in industry. So you typically design components that then are integrated together in the final system. I was planning maybe towards the end of the course to give you also some perspective on component-based design, testing, and automatic code generation, things that are used in industry. Let's see if we will have sufficient time to do so. Okay? In that case, we will also see a little bit of this component-based design part. We need to guarantee predictability and safety, ISO 262, for instance. Look at the number of ECUs, embedded controllers that you have in the car. These are very small processors, okay? One core, maybe two cores sometimes, but these are very simple processors, okay? Simple cores, running even very low frequency, 100 megahertz, if not less, okay? So when I was born, there was maybe one or two of these controllers in the car. Now you can see the exponential increase. If you buy the latest Mercedes, you have more than 100 ECUs in that car. 100 systems, okay? Sparse around disseminated around the vehicle in all different parts. For cluster, chassis, engine, gear, steers, lighting, comfort, belts, if not to autonomous driving, even before coming to autonomous driving and ADAS, advanced driving assistance systems. There are really an exponential increase on those. Look at that. So this is the ECU adoption in automotive. So you can see the number of ECUs. This is just the latest 5 years, which is constantly increasing. And here you see the domains inside the car. Safety systems, powertrain, entertainment, which is getting larger, chassis, electronic, and communication and navigation. Okay? You will see it better in the slide deck, but typically you have a backbone, communication backbone, typically a CAN bus, a FlexRay, or whatsoever, connected with hundreds of ECUs that need to communicate among each other. Okay? So it's a heavily dense and heavily difficult to solve problem to do that reliably and predictably. Okay? So in 2010, the Range Rover had 40 ECUs. In 2014, it had 98 ECUs. And all of these ECUs need to comply with timing requirements. Different requirements, of course, and this different safety level. So this norm here, this regulation here, specifies different safety level. For the automotive, this safety level are called A0, Automotive Safety Integrity Level. Okay, and these are classified from A to D. Okay, A0D is the most critical one. Okay, for instance, steering or ABS or EPS, this kind of system are A0D. Okay, nothing can ever go wrong. Okay, A0A, yes, still it is critical, but not as critical as D. Okay, what is not critical from a safety integrity level is called QM. Okay. And of course, this was about the hardware, but what about the software? You may have guessed, if the hardware increases and gets more complex, so does the software. So, you can see that in terms of just lines of code, lines of source code, okay? From the 80s, we had more or less 1,000 lines of code, which is more or less your project, and my first year guy's project. And now we are here, so 2000, okay, this is 10 to 9, okay, 1 billion lines of code. How can I assess the predictability of such a system? Okay, it's a mess. And the same in the avionic domain. In the avionic domain, the current Boeing, the current Airbus had around 100 million lines of code. 100 million lines of code. Not all 100 million lines of code are safety critical. In the avionic domain, the safety integrity level is called DAL, Design Assurance Level. And the norm is DO plus a number that you don't need now to remember. But you have the same problems in the avionic domain. Okay? So in the automotive domain, what are the typical functions? So engine, the ECUs that govern the ignition, the fuel pressure, water temperature, the valve, gear control, all these are related to the engine. Okay? And typically all of these are either D, C or D, so highest criticality. Dashboard, the cluster, the display, also many of these have very tight real-time requirements. So the cluster should have guaranteed, I think by heart it was like 60 or 80 hertz of refresh rate. Diagnostic, safety, you know, the automatic braking system, the ABS, okay, that recognizes when it should come to play. The stability control, and so on, for those of you who are familiar with automotive dynamics. And then, it's getting more important, the assistance. These functionality were not included 10 years ago, but now power steering, navigation, sleep sensors, parking, night vision, collision detection, all of these ADAS, Advanced Driving Assistance Systems, are commodities in today's car, okay? Comfort, and so on. So you can guess that I'm not joking when I say that there are 100 million lines of code in your cars. So, okay, this was already said. But what happens when you have more lines of codes? When you have more lines of codes, the number of bugs inevitably increases. You may be the best programmer in the world, you may be Linus Torvald, you may be Stallman, you may be whoever you want, but you will make mistakes. It's very, very difficult not to make any mistake when you write more than 10K of codes. Okay? The Linux kernel is bugged. Today, we just didn't discover all bugs. You know, we corrected most of them, but there is not any confidence in being it bug-free. And the more line you increase, and the more bugs you insert. And they are not linearly dependent. They are exponentially, quadratically. So if I add 10 times the lines of code, the number of bugs will increase by more than 10 times, because there are all the interrelation among the lines of code that you insert. Okay? So imagine if you have 100 millions of lines of code, the number of bugs really explodes. So you should make sure to use mechanisms. It will not be the subject of this course, but the system will need to be able to recover in case of a failure. Or at least you will need to confine, to isolate any possible cause of failure within that particular domain without making the system collapse. Okay? This is getting more and more important in today's system. Okay? So reliability, when you have a 10 to 8 instruction, is becoming a problem. So how do we guarantee the reliability of such a heavy system? So reliability, of course, does not only depend, as I said, on the functional correctness. Reliability also depends, in this system, by the temporal correctness. What if I need to wait too much time between braking the pedal and the braking being placed? Okay? What if this t plus delta, what if this delta is too big? There is no need to explain, right? So, and here is a controller. Everything is mediated, okay? There is not a direct mechanical cause on the braking to be into place, but it's mediated by a controller here. Controller takes time to control, okay? So we really need to make sure that the timing is correct. The danger of it may vary between being the functionality useless, so maybe I miss a frame, no one dies, to be even dangerous. Okay, so if in this case, if it is too late, it really becomes too dangerous. You may know about some of the massive recall of cars that have been out in the latest days. Multiple of them were due to problems of these kinds, that the functionalities was not implemented guaranteeing a timing correctness. So the response time of our real-time systems must be bounded, so there is a bound on the response time, and predictable, so I should be able to compute such a bound for this kind of system, because then I need to go to the certification authorities to provide evidences that the program, that the application meets that requirements. So the predictability must be guaranteed for each single task, not for just one. If you have 10 tasks and 8 of them are at hard real time, you need to provide that all of them, in any possible way they might combine, it will never happen that one of them executes beyond the deadline for all possible combinations of events. And this, you guess, is difficult to test. There is a trade-off between efficiency, throughput, performance, and predictability. This is the typical trade-off we need to face. So our cores, our general purpose laptops, desktop, are designed for efficiency, for throughput, for performance, for average performances, not for worst case performances. So our cores, our operating systems are designed for the laptop, for our machine to get fast on average, okay? On average, I don't want to wait too much for our task to be finished. In a real-time system, it's not the average that matters, it's the worst case that matters, okay? Your system should be designed so that the worst case may never be worse than a given deadline, okay? It's not the average that counts. So efficiency has to do with throughput, with performance, okay? Predictability has to do with worst case conditions. So these are typically trade-offs. Just to give you an example, the companies we work with, I'm not making names, but these are huge industrial automation companies. They use multi-cores. So their control system are typically x86 architecture, okay? And they use quad cores, okay, for their system. Now, fine, but how do they manage predictability? Well, it turns out that they turn off 3 out of 4 cores to achieve predictability. So they buy multi-core, because it's the only thing that you can buy nowadays, okay? They turn off 3 cores, and they use just one of them to ensure predictability, okay? So this is the situation. You sacrifice efficiency, you sacrifice performance to achieve predictability, okay? So here, you can also do the other way. So I use all 4 cores, but the worst case can take forever, which is what we do, right? Sometimes it's not a good example, but sometimes it happens to you that the laptop takes forever before opening something, okay? So what we are trying to do as a group now is try to have predictable performance, okay? You need to use some new techniques that are not yet implemented at OS level, okay? It's not part of this course, it's more part of the research we are making as a group, okay? So just to understand the performance versus predictability trade-off. So again, the way an embedded controller is made. The sensors are your interface to the environment. The actuators modify the position and the relation and what your system does inside your environment. So there is this loop, this feedback loop that reads, modify, reads, modify, reads, modify. You may have communication with user-controlled monitors, desktop, or whatsoever, or with other peripherals. Okay? This is the typical embedded object. What distinguishes an embedded system from general-purpose computing system that we are used to take a look at? So in an embedded system, you don't have all the resources you want. An embedded system typically have a much shorter amount of memory than your laptop, okay? You don't have terabytes of memory, okay? The memory is small, so you need to optimize across the memory domain. Space, weight, time, memory, and energy. So it's much smaller than the SoC that you have there, than the system on chip that you use. The weight, it should weigh less. You cannot bring a PC in your pocket or in your car. The time should be predictable, so most of the performance optimization hardware features that you have in your Intel laptops are not used in embedded controllers because they increase average performance, but they decrease the predictability. Example, the Intel has a lot of out-of-order executions, okay? Has a lot of branch predictors, have a lot of all this kind of fancy stuff. But this fancy stuff increases the average performance, but in the worst case, these out-of-order execution engines may lead to a very pessimistic worst-case response time, okay? And instead, embedded controllers that you use, for instance, in automotive, are much more predictable. They just do their job, and they do it predictably, Okay? They're not interested too much in increasing average performances, sacrificing predictability. Memory, I just said, and energy. This thing here, maybe this is power optimized, but the desktop that you have at your home consumes around 100 watts. If you have a fancy GPU in it, if you have a gaming platform, it may go up to 500 watts. Okay? Well, the system on chip that we are using for autonomous driving now, so this is the heaviest, by order of magnitude, heaviest and more power consuming controller that you have in the car, consumes 10 watts. The vast majority of controller you have inside the car is below 1 watt. Okay? So the energy should be much smaller than the energy that you consume in general purpose computer. Okay? This is also typical of embedded systems. You don't want to add a fan for every of these 100 controllers that you have disseminated in your car. Okay? Typically, you don't want to add a fan, a cooler, a cooling system in your car. Okay? So, in order to meet these constraints, you need to provide algorithms that have a high efficiency in the resource usage. Concurrency. The system that we have in an automotive, in a car, are inherently concurrent. One of the standards that are adopted is called AUTOSAR. AUTOSAR specification typically have tasks, multiple tasks, each one with a different period, and inside one task, maybe the 10 millisecond tasks, I have different functionalities executed one after another. These are called runnables. Okay? So I have concurrent tasks. Each task have a runnable. So I have plenty of concurrency inside an automotive system. And I need to guarantee the temporal isolation, as we said. An embedded system interacts a lot with the environment. It has many sensors and interaction with the environment than your laptop. The sensor of your laptop is the keyboard, is the only sensor, the only input, the way you generate input, and the mouse. Okay? In an embedded system, typically sensor modify the way this embedded system behaves. Thinking about an autonomous car, you get what I mean. And a high variability on workload and resource demand. So this system should work in every possible condition. So I need to design my system such that it works in every possible condition. So I have to design it according to a wide variability in the inputs that can be given to such a system. Okay? So the system is the entity to be controlled. Okay? The controller is the ECU, is the core, is the CPU that modifies the trajectory, the actuators, or whatsoever. Okay? We will not design controllers. It is not the main work, the main task of this course. I don't know if you guys gave controlli automatici. Okay, so you know what the basics of control systems. Okay, you know the equation, all the relation, feedbacks, loops, and stuff like that. This is not the object of this course. The object of this course is to give a controller how to implement it on a real system. Okay. So the controller sends signals to the system according to a predetermined control objective. This is our controller that sends the above signals. So what you studied in automatic controls, controlli automatici, is this guy that writes nice formula. He designed the model of the system. He designed this feedback loop. Designed some nice or fancy control strategies, zeros and I don't know what. Okay, so it provides the control equation, for instance. What we do here is this guy here. So we take the math and we bring it into practice. Okay? So, and this is true in industry, that these two guys never talk to each other. Seldom talk to each other. So typically you have a control group, and then there is a system integrator that just bring the stuff together without talking to them. So you will be given control equations, models, and stuff like that, and you will be asked to integrate them, and they will tell you, please do that within 10 milliseconds, please do that between 5 milliseconds. And if you're particularly unlucky, they will ask you to do sub-millisecond, like Ferrari is asking us to do. Okay, so going below a millisecond in the control loop, it's a mess in current architecture, okay? Because there is a lot of unpredictability that you need to take into account. So this guy here typically assumes that you have the best computer ever with infinite memory, infinite resources. It runs like hell, okay? You can do whatever you want. Instead, you very well know that this is not the case, okay? So we will need to schedule the scarce resources that we have, okay? We need to make the most out of them. So in reality, the embedded system that we said has limited resources, have finite bandwidth, finite memory, finite computational power. So a control application will not be executed right away. It will take some time to compute and actuate. Okay? There are several activities that may be concurrently scheduled, and there are variable delays. So what the old guy assumed earlier in the equation, so writing control equation assuming that the effect is immediate, will turn out not to be true in the practical system that we do. There will be always a delay. The larger the delay, the wronger the assumption of the control guy. The smaller the delay, the tighter could be the control assumption. Okay? When I design my control system for steering my autonomous driving model for that curve, I assume that what I read, what I sense, is exactly at the moment that I want to steer. Well, this is not the case, we told, okay? So this delay invalidated the control assumption. So the car will not follow the path that I wanted it to follow, but it will be different from what I assumed. Take a look at a physical example here. This is an inverted pendulum. What is an inverted pendulum? It's like you have a trolley, you have a small car, okay, with a stick on top, okay? The gravity, the stick is incinerated here, and okay, this is the only connection between the stick and the car below, right? So gravity, of course, would cause the stick to fall in one direction or the other, right? Unless you take some preemptive action on the truck, on the car, on the trolley, okay? So if the stick falls this direction, then you run this and you re-equilibrate. And if you accelerate too much in this direction, it will go the other way, okay? So it's a control problem. At the end, if you properly tune your system, the stick will be in the right position, horizontal or a given angle. It can even be different than the perpendicular one. So typically, your only actuation is in this direction, and your sensor is the angle of the stick direction. Okay? So this is your sensor, and this is your actuator, the simplest possible control loop that you may figure out. Okay? So what is your controller doing? Very simply, if this is positive, we will give a positive push here. Okay? This is positive, we'll try to equilibrate it here. If this is negative, I will try to move it in the other way. Okay? This is negative, this will be negative. So this is a very simple inverted pendulum controller. How is a control task written in this sense? Oh, I'm already too late. Okay, let's try to finish this slide. So how is a control task written in this sense? So you see code, right? You're given a theta angle, so this is the reference angle, so this is the angle that you would like the stick to hold, okay? And this is the control gain. So this is your system. You have initializing the error, u and theta, and you essentially have an infinite loop. When I told you before that a real-time system is not just one task, one simulation, one batch to complete, but it's a recurring activity, okay? This is a recurring activity. You will have, in our program, you will have a lot of while one Okay, go forever. Okay, until I tell you to stop. Okay, this is the classic way systems are done. So what do I need to do iteratively? I need to read the sensor, okay, read the sensor and put it into theta. Okay. Then what do? I compare the theta with the given objective target angle. Okay, this is the arrow. Okay, if you did controls, you know what that, right? This is the arrow. And typically, what do you have? This arrow is multiplied by a gain to give the actuation signal. Okay? If the gain is 0, the arrow will not have any effect on the actuation. If k is huge, then a small arrow will come in with a very strong push. Okay? So, and this will cause an output. I will enforce the computed actuation signal. And then I will either just continue doing that, or what we typically do, there is no need to take so often control decision. We will just wait for the next period. This is a synchronization event. You may wonder, why do I need this? Can you try to answer this question? Why do I put here a synchronization period? What can be the reason behind it? If I didn't have that, it would just continue doing that, computing and computing and computing and computing. Having this, what do I gain?
Data from sensor.
Say again?
Data from sensor.
The data from sensor comes even without this. Now it will keep reading the sensor and controlling, reading, controlling, reading, controlling, reading, controlling.
To complete the action.
Yeah, the action is completed here, right? It's an output. It's reading, enforcing, reading, enforcing, reading, enforcing, reading, enforcing with no break in it. Is it really necessary to go so fast? Probably not. Probably there is no need to case so frequent actions. The system has its own dynamicity, okay? Probably if I take one action every 10 milliseconds, it's enough to control the system. If I put a synchronization here, okay, wait 10 milliseconds, wait until 10 milliseconds are passed, I'm sure that every 10 milliseconds the proper action is taken. What do I gain in this sense? Again, that the CPU, the core, is not exclusively used by this controller, but I can put here other tasks, other concurrent tasks. If I don't put this, I waste one CPU just for doing this. There is no break here. It's a continuous loop. It's a while one. There is no break in it. It will not turn off. Okay? It will just continue, 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 continue. And if there is a preemption of another task, the control gets stuck. Okay? Doing this, you accommodate some slack, some idleness to schedule other tasks. Okay? Do you make my point? So real-time tasks are done like this. Okay? Action and wait for next event. Action and wait for next event. Our target is to complete this action before the next event comes, more or less. Then the deadline can be different in the period, or we'll talk about that later. Okay? I think that could be a convenient stop for today. Thank you guys for the first class, and I'll see you guys tomorrow.